web page, the course web page for grading. It specifies how the grading is done. And so depending on whether you're taking it for 1 or 2 credits or 3 or 4 credits, it's different. 1, 2 credits, it's half homework, half class participation. And for if you're doing 3, 4 credits, then class participation counts as less. I think it's like 10%. Homework is less, but then there's a class project too. The number of homeworks that are required depends on how many credits you're taking the class for. So if it's 1 credit, it's actually only 4 homeworks that are required. You can turn in more, and we'll just take the top scores. And then it's 4 times the number of credits. So for 4 credits, it's 16 homeworks. Again, there are 20 classes, so that would give you, we only take the top 16. Okay. Other questions before I get started? Administrative stuff? I have a little bit of administrative stuff that I wanted to cover as well. So here we go. All right, yeah, so, okay. I'm still having that problem with it cutting it off, but it doesn't seem to be catastrophic. I'm not going to fool with it. All right. Okay, so here's about the homeworks. Kenneth has done a lot of the grading so far. Make sure you close it all the way. Thanks. And there's a sign-up sheet for class participation, so please make sure you sign it. All right, so as you can tell, I sort of randomized the orders. There's no identity associated with these. But this is all the raw data for every student who's registered for the class. And you can see that for the first couple of classes, people did quite well. And this is, I didn't label this, but this is homework 1, 2, and so on. So, we've got good averages here from 1 and 2. And then it falls really fast. Part of that is due to the number of people who are not turning it in. Okay, so you can see that a number of people are just not turning in homework, and maybe there are people who are taking it for fewer credits, but it is a concern. So I haven't. I mean, initially, early on, there were people who were coming to office hours. I've seen a little less fall off. Dave, what has been your experience? I guess this last week was sort of an odd week for you. Yeah, yeah. So you can't really judge. And Kenneth isn't here right now. Yeah. So I mean, that's another consideration too. Is there are people taking advantage of office hours? The other thing is sort of anecdotally, it seemed to be that one area where there's some confusion and some of these homeworks sort of focus on that might be functions, that particular topic. All right, so I see some nods on that. All right, yeah, and since, okay, so I'd like to spend just a minute or two and try and probe, because I have some ideas about where the problem might be. Kenneth had some ideas too from his interactions. So let's try and see what registers in terms of where there's confusion about functions. So a source of confusion I've heard is, well, when do you create a function? For what purpose? What is it supposed to do? Another source of confusion was sort of the mechanics is how it works. What's the syntax for describing a function in MATLAB? And now we're into Python, so we also have Python functions too. And actually, we're going to be talking about object-oriented programming, and much of an object are methods, and methods are functions. So this notion about how do you declare what a function is, what its inputs are, what its outputs are. In MATLAB, the outputs are specified explicitly. In Python, they're not. So I didn't know if that's also a point of confusion. A third one, which I haven't heard explicitly, is how do you use a function? I mean, I think you're probably familiar with using functions because much of a language like MATLAB is using functions, like plot is a MATLAB function. So any comments or insights about this? I know sometimes when you're confused about something, it's difficult to articulate a clear question because you're confused. And I sympathize with that. So I'm not expecting you to explain in any articulate way. But those of you having some problems, yeah, let me know, please.
I actually spent an hour with Kenneth and we kind of went through functions with him. And the output, right? So you put these things in brackets. That was kind of confusing.
Okay, so the way you get the output from MATLAB, yeah, MATLAB especially where you can specify sort of a composite output. You might have like 2 variables output. We did that, for example, with Michaelis-Menten, where we had Km and Vmax. Those were 2 outputs, and you had to specify in a particular format. Okay, that's a good one. Any other comment about confusions on functions? So that was one. So it's where the output works, especially for a complex output.
I guess the theory behind it, when he told me that it was just a math function, that it was y equals f of x.
Yeah, okay, so that makes, right, okay. All right, so maybe the concept of what it is, what it means. Other comments for anybody who, again, this is helpful because what I'm thinking about doing is maybe, if it's useful, I could create a special video, video just on functions, but I'd want to address the points of confusion, and so I need some input about that. Look, if you want to reflect on this a little bit more, send me an email and let me know. Yeah.
Well, in functions, you often do you do loops and stuff in functions?
Yeah, absolutely. Anything, a function is just, okay, that you can do the same operations, like you could have loops, you could have conditionals. That's it. Just make sure you close the door all the way. Right.
So like talk about like for loops.
It's not closed. You're gonna have to pull it because it doesn't. Yeah, it doesn't close on that. Thank you.
If you are going to do a video, really talk about for loops and while loops and iterators and stuff like that. Those things are when I was trying to write functions, I didn't even know where to start or stuff like that. So,
Okay.
And I might be in the minority there, but
Okay.
if I wanted a video from you, that's what I would.
Okay. Yeah, go ahead.
Possibly like an introduction to the less common do while loop as well.
Okay, I'll see about that. I mean, I'm not holding you responsible for anything other than what we present in class.
Okay.
Yeah. Okay. So I heard that complex inputs, outputs, that what's in a function, that you can do anything in a function that you can do outside. Okay. Anything else that was a point of confusion with functions? Okay. All right. And again, make sure you're getting help when you need it. If you're confused about something, not turning in a homework is probably not going to help you learn it. So, all right. Okay, Kenneth, all I was doing was going through and reviewing. I put up your stats, sort of randomized the order of things, but I presented the raw data, so it's very clear that there's some issues with homework. Did you have any other feedback for what you're seeing when you look at the homeworks?
Well, many people seem to avoid using functions or use functions for very, very small tasks. And it should be used to complete, well, one goal, but it should be smaller than calculating the mean or something. But,
Okay.
yeah.
Okay, so I mean the comment, I'm just going to make sure I get it on the recording. So the comment from Kenneth was that he's seen people use functions for very small tasks. And I think that may go hand in hand with this confusion about what you can put in a function. And maybe that the thought was it was just a simple calculation as opposed to functions can be quite large. I mean, generally you don't want them very large because you want it to be understandable. But what you do is you have a function call other functions. And that's the way you sort of break down a program. That's a basic principle of how you design complex software, is you build up sort of these layers, and you have functions calling functions calling functions. Okay? Other questions or comments? Okay, good. All right, so, okay, so today's lecture is going to be about, you know what, I think I missed one slide here, which was, hang on just a second, what did I, okay. I guess I put it in the next lecture. Well, that's okay. I'll just mention this as a forward reference. So the other thing we haven't talked about yet is the class project. We've gotten we've gotten more specific about that, how we're going to do it. Details of the class project are now available on the course webpage. If you go, there's a link on the side. On the navigation bar, there are two parts there. The bottom part says other links. There's something that says class project. If you follow that link, you'll see a write-up about 2.5 pages long that describes the class project. The class project is required for anybody who's taking the class for 3 or 4 credits. If you're taking it for 1 or 2 credits, your role is going to be a slightly different role. You're going to be a reviewer. You're going to get to evaluate, design and presentations. But it's required for people with 3 or 4 credits. I sent out an email to those students who are taking the class for 3 or 4 credits. It's going to be done in teams, and so I wanted to see if you had preferences for who your teammates were. And so hopefully you've completed that survey, and we will be then putting together teams. We want to try and balance the teams so that, based on the homeworks, we don't want to put together students who are, seem to be just having problems based on the homework. We'd rather, have people learn from one another, ideally even complementary. We'll talk about the class project a bit more the next couple of lectures. I think it's in 2 weeks. We'll actually have 2 days that are just devoted to the class project. Make sure you pull it all the way close. It's got to shut all the way. Okay. Make sure, yeah, that and we'll get a lot more detail there. By the time, what we're hoping to do is that the first part of the class project, which is doing I'll talk about what this means today, a functional spec and a design spec. That part will actually be done in class, and you'll actually present it, or a good part of it will get you started in class. You'll actually be presenting it in class, so that will be coming up very soon. So look at the link, take a look at those write-ups. We'll talk about it a little bit on the day that we introduce the class project, but you're going to be so far ahead if you've already read the material and see if you have questions. Our assessment is that the coding part of the project is not very challenging. We're expecting that because we know we have not been very deep on coding intentionally in this class, because this is not a coding class, it's more of an engineering class. We're trying to give you the ideas of things in a more holistic way. However, the sort of the process you go through, this notion of you think about what it is you want to build, that's called the functional specification, and then you figure out how you're going to build it, that's the design. Those are the things we're emphasizing, and then the whole management of going from the design to code. That's what we're more interested in. Any questions so far on the class project? Do take a look at that link. Okay, good. All right, so design. What do you think about when you think about design? Yeah, any comments? Yes?
Is the design really intuitive?
Intuitive?
Easy to follow?
Follow? I'm not sure I understand yet.
You're designing something that appealing for other people.
Okay, you want something that's going to appeal to other people. Okay. All right, so especially with something which interacts with a person, a human being, like interactive design or user interface design. I think that's a very common kind of view of thing. How about if we're building something that's more of a back-end piece, what people would call plumbing? So, the analogy is like to a kitchen. I have my faucets that I turn off and on, and the user interface is pretty easy. I have a knob or I have a handle. That's my user interface. But underneath, there is, all the pipes that went in there, and water has to flow through that stuff. That's sort of the how it works. What it does is it delivers water, and that's what we call the functional piece. The design part is how it works. Okay, so, a car. Cars, the other analogy is a car. I mean, generally, cars generally have a steering wheel. I guess if it's an autonomous vehicle, it might not. But, generally they have a steering wheel, they have a brake, they have a gas pedal. That user interface is pretty standard. But the design is, really what's under the hood. What's the engine look like? What's the carburetor look like? What's the drivetrain look like? What is the propulsion system? What energy sources use? Is it gasoline? Is it electricity? That would be more about the design. So in terms of software, here's the way we break it down. We're going to create what's the term software artifact. I don't know, have you heard that term, software artifact? Is that something familiar? So one example, it's something you produce. An artifact is something you produce. And a software artifact, obviously code. That's a software artifact. Another thing is documentation, anything you write up about the software. And a third thing, which I haven't mentioned yet, but is probably the most important part of a software system that you folks will face. Have any idea what that might be, what I've left out? Data. What is that? Don't really think about this. What is the design of your data? How is it organized? Is it put in tables? Are there many tables? How do you label the columns? Do you know the types of data that are in each column? That's also part of your software design. So creating these software artifacts are intended to accomplish a goal. That's really important. A lot of times everybody's heard the term hacking, okay? And it takes on sort of a negative connotation. I mean, it's actually an exploratory exercise. I think the term cracking is a better term for something that's a negative thing, with all the security breaches. But hacking is basically you're trying to sort of explore something. So it's very easy to create software by just sort of noodling around or exploring. That is not an intentional system. It may lead to something where you figure out what you want. But at the end of the day, when you have your software system, it does something. So like your kitchen sink, it provides water to you. And the way it does it is you turn the faucet on or off. If you have, the programs you wrote for the Michaelis-Menten enzyme analysis, they do something. Given this data of reaction rates and substrate concentrations, it tells you, it fits a curve to the raw data and estimates the Michaelis-Menten constants. It does something. So you got to be specific about those goals. And the way it achieves this is by properly constructing and interrelating primitive components. In other words, you start from something. I may be going to start by having the Python language or the MATLAB language. I'm going to maybe I'll get a toolbox or two to go. What are my primitive components? Why is it important to think about the primitive components? Anybody have some thinking about that? Have you heard the term dependency or software dependency? Anybody try to install software on their computer and it doesn't work? Okay, almost all the time, that's because of some dependency. There's something on your computer that you need to have and you don't have. Or there's something on your computer that you shouldn't have and you do have. Those are dependencies. And so those are the things, that's why and a lot of times you will see an equivalent system being created, equivalent in terms of the goals. But it's done in a way so it has different dependencies because those dependencies are either better quality, they're less expensive, they're easier to update, something like that. So that choice of primitive components is really, really key. So some of the challenges in software design, as in any design exercise for that matter, are first of all, well, what are the pieces of the system? Okay, so I'm assuming I already have my goals. That's my functional specification. I know what it's going to do. I'm going to do Michaelis-Menten analysis. I'm going to do flux analysis. That's what I'm going to do. So then I've got to figure out what are the pieces. Okay, so those are the components. And either these are primitive components that I've gotten from elsewhere. Maybe I've found a MATLAB toolbox, or I've gotten a Python package. Those are the things in my primitives. Or the things that don't exist or I can't find or are too expensive. Maybe it's a program product that I have to spend thousands of dollars to get, and I don't want to do that for the little piece I need, so I'm going to write it myself. Okay? So these are the individual components that I have to construct, and I have to specify them, describe them, and potentially build some of them. And then I have to figure out how the components are going to fit together. Much like if I have a car. I've got to figure out where the engine goes, where the carburetor goes, where the exhaust goes. I've got to fit the pieces together. Then I've got to figure out where it is I'm going to get these primitive components, and that's this whole dependency structure. Okay, so that's sort of an overview about what software design is about, and it will lead us to a certain sort of approach or strategy to going about it. So I'll say a little bit. I'm going to go through and talk a little bit. A lot of times, I assume that I know from your class roster list, the class roster list, nobody here is a computer science student. So, and that's fine. I don't think any of you have had formal training. Maybe have taken maybe one computer science class, most likely not even any. And so this whole notion of designing software, I think, is sometimes sort of foreign because largely those of you who've had experience, you're self-taught, which is great. I mean, and I will tell you that being self-taught in software is absolutely essential. If you are given a foundation in some formal way, and after that, everything is on your own. And that's why we've really emphasized in this class figuring stuff out on your own. We don't give you a standard environment to do Python or to do MATLAB. We give you links to go out and install stuff because that's part of the experience, an essential part of the experience. So a lot of times people don't get this sense about, well, why should I do more than just exploration and build what I need to build? And design is actually a key part of this. Then I'm going to talk about one particular kind of design called object-oriented design. It's been around for a couple of decades. There are other design techniques, but this particular framework I find is relatively easy to understand and immensely powerful for what you want out of a design system. And so then I'll go through the various elements of that, the key elements that I think are important for this class, and that is, in object-oriented design, how do you specify a component? How do you talk about how the components interact? And then, most importantly, which I seem to have neglected over here, there should be one up here, how you describe what it is it's going to do, what's called a use case. So apparently I skipped that one, my apologies. The next thing I want to do is, so design can be a descriptive exercise. It doesn't have much value unless it gives you sufficient detail so you can actually write code. You can actually build something. It's much like getting instructions for putting together something. I know I would go to these sometimes, when my kids were young, we would buy these kits like that, put together a chair, and the people who had written the instructions didn't spend a lot of time on it. And so trying to figure this out was a real challenge. I mean, it required a lot of intuition. So those were not good specifications. They didn't really tell me with great clarity, at least not me. I mean, maybe it's a function of me rather than the instructions. But that's the whole thing, is you want your design, the way you describe it, to be something that others understand so that they can actually build software. And you can share with others about what it is that you've done. And very important issues. Okay, so why design? All right, so what I'm going to do is these are just eye charts, and I want your reaction. Okay, so I'm going to show you a couple of designs, and you give me your reaction to it. You know nothing about these systems, and they're all visual. So, okay, so here's one design. All right, pretty much know what's going on there? Got the idea? And assemble that in a jiffy, right? Okay, all right, here's another design. Okay, now, what are the things that are different? Again, these are eye charts. You really don't know anything about those. The first one was a lab automation system. It was actually a graphical system for describing interactions between components. And the second one here is sort of a classic computer science architectural diagram. But if you look at the difference between these two and you ask, what makes a design understandable? What are the kinds of things that gave you that gut feeling about, with the first one, oh my God. And the second one was, yeah, I think I could sort of parse that. You think about those kinds of things that struck you that made a big difference? Yeah.
Lots of long lines.
Yeah, lots of long lines, lots of connections, interactions, yeah, yes.
Everything was just kind of too compact and not separated whatsoever, so it's hard to determine exactly the structure of the...
Okay, all right, so that's a really good one. Everything was sort of mixed together. There wasn't really a structure to it. You couldn't tease it apart and do sort of a divide and conquer to figure out how things fit together. Any other comments? Those are both very good, by the way. Okay, well, I think you pretty got some of them. So I'm going to actually generalize this notion of the piece parts, and that is what I'm going to call abstraction hierarchies. And that is that you have something that works at a high level that does like a high level goal, and you divide that up into sort of like next level goals. Like I want to create Google Maps. Okay, so what do I need to do? Well, I need to be able to relate pixels across the planet to areas across the planet to pixels. And how do I do that? I can divide it up into regions. Okay, so how do I get those regions? That becomes a next level concept. So what's a region? And so on down. That's a use of what I call abstraction hierarchies. And the second one is that there are few interactions. So you would like to have that, which means that probably you don't have that many components. And this is a matter of sort of judging. How many levels do you have? Because if it takes 1,000 pieces to build something, you're going to need the 1,000 pieces. You don't have a choice. But do you put all 1,000 on one page, or do you try and group them together? Maybe there's a level of 5, but then each of those 5 has another 5. Well, that gives you 25, but then you need another level. Whereas if I started out with 10, potentially go down. So there's a certain amount of judgment about what levels, how many abstraction hierarchies you have. There's another thing that is extremely helpful when you look at a design. Can you think about what that might be? Yeah. Labels, yeah, right. Certainly you would want to label them. So the other thing is, you as a human being, when you look at something, if it's familiar to you, that makes a heck of a lot of difference. In visual interfaces, and I think that was one of your comments earlier on, you were thinking about visual interfaces and interactions with them. Yeah, right. So in visual interfaces, there's certain things you expect. When we look at a web page, we expect a menu bar. We expect something that, some text boxes we're gonna enter some text into. Is it familiar to us? If I designed a car where the steering wheel was, let's say, at my feet, and I moved it with my feet. Well, that would be pretty bizarre. I'd never seen that before. Okay, so if it's familiar to you, then that makes a heck of a lot of difference. There's this notion, which I'm not going to go into much today because it's more of an advanced concept, but something for you to keep in mind as you progress with using software. And something called design patterns. And it's done at various levels of granularity that, even from, a single algorithm to something which is an entire system. There's something called an observer pattern, a policy pattern. There's a bunch of these that we'll talk about. And this was actually a significant evolution in software design that happened in the 1980s. So this is the whole notion of when you design something, if you do it in a way so that others have seen something similar, it's going to be easier to understand. All right, so there's a lot of philosophy, but I think it, hopefully it also motivates why it is we're interested in design and why it is we just don't, try and write code directly. And so if you design something well, software well, it provides this notion of, you have isolated pieces that you can sort of do a divide and conquer. You can divide up the project and you know how things interact. And so that really helps a lot. A lot of times, if you describe something in a way that others can understand, then a lot of times you realize, wow, this can't work. I've got to fix this or do it in a different way. And you know what's neat about that? You haven't written a single line of code. The best bugs to find are the bugs that happen before you write any code. Those are the best ones. The longer it takes to figure that out, the more energy you've expended, the more complicated it is, the harder it is to fix. And I mentioned people working in parallel. And the other thing is when you get isolated components, it's easier to test them. Okay, so this is basically philosophy, but I think it's helpful to sort of set the mindset. Now I'm going to get more into specifics and talk about a particular kind of design methodology. There are many, but I said before that this is one that's been around for a long time, and I think that I certainly am a big believer that this provides tremendous value in terms of the time spent doing it. Okay, so let's do this in a specific context. We'll do this in the context of some kind of lab informatics. Okay, so we're going to do a few things in our lab. We've got a whole bunch of experiments that we're running. It's, biochemically oriented. We're doing some enzyme analysis. We're doing some flux analysis. There's this general reaction rate analysis we're going to do. We're doing all this stuff. And so we're going to have to design some software here that, really, there are probably multiple applications even. They're going to do all of this. All right, so that's sort of the space in which we're working, and you could say that each one of these is a different application, and each one, when we talk about design, we have to first of all talk about what's the goal for, let's say, the enzyme analysis application, and then what are the primitive components and how do they fit together, and we'll have to think about that for all of them. Okay, so I'm going to talk about this object-oriented design process, and so it's described as a system of interacting objects. Now, we came into contact with objects last lecture. We talked about Python. We talked about really the mechanics around objects. A class, which is a way of describing a template for objects, and objects are an instantiation or an instance of that template, just like you would have like a boilerplate that you would fill in. You have various blanks. Or anybody ever hear Mad Libs? You familiar with Mad Libs? Yeah, similar kind of idea. The Mad Lib is the class, and when you play the game and you fill in the blanks, well, that's the object. Okay, similar kind of idea. All right, so we've got this notion of interacting objects, and that's the way object-oriented design is going to be viewed. Okay, so objects contain data and procedures. Procedures in this case are methods, and we saw that last week. There's what's called the interface, and that's how you interact with the object. For example, what's one way you interact with an object? Well, actually, the class. You got to create the object. You do the constructor, right? You say, Joe car is car that is... It's blue, it's a sedan, it can go up to 100 miles an hour. That's one part of the interface. How do you construct it? Okay, and then an object-oriented program describes this interaction. So we can see that this is going to satisfy the elements of the design that we want, because we've got to talk about what are the components. So our components are going to be objects, and objects are created from classes. So what we care about is, can we describe those classes and how they interact with one another? So we've got the classes, and then we've got to figure out what their interactions are. And once we've got the classes and the interactions, what do we want to do with all of that? And for the design, to sort of verify that this design is doing the right thing. We want to make sure that those interactions with those objects are able to achieve the goals that this software system is supposed to do. So let's say we're doing Michaelis-Menten enzyme analysis, and we come up with four objects that are going to interact from 4 different classes. All right, we want to make sure they can actually produce the plot of the fitted curve to that raw data. It's going to estimate Km, Vmax, and it's going to actually produce the plot. Make sense? That's what we have to do with this. Okay, so here are the steps in object-oriented design. Okay, so the first thing is, remember that thing about what are the goals? Okay, so this is synonymous with what are the goals. What does the system do? I'll use that sort of interchangeably. That means what are the goals? And anybody here heard the term use case? Okay, this is such if you talk to a software engineer about building something, you will right away, if you don't hear that word 5 or 6 times, ask for that person's credentials. I mean, have they really written any software before? Yeah. So use case means, what are the things I have to do as I'm interacting with the system? What is it going to do for me? Like Michaelis-Menten analysis. I've got to estimate Km Vmax. Is that what I'm doing? Sort of like the perspective from the user. So that's the first stage. And there's actually, in the methodology I'm going to describe to you today, all of these steps come with their own diagrams. And that's actually part of what you'll be dealing with as well. Not so much creating them, because this does take a little bit of time to digest. But I want to make sure that you can read the diagrams so that you can understand them. And so that's really that's what the homework will be about. Be able to interpret those diagrams and translate that into code. It's a good specification. You should be able to do that. So these use case diagrams. Then the next thing you have to do, you have to specify the components. We know what the system's going to do. Now we have to figure out the components. This is exactly what we said up front in terms of the objective of the design. Specify the components. Okay, and so then the next question is, well, how do you specify components? And in this methodology, there are particular ways of doing it. Well, we know that our components are going to be objects, and objects are described by classes. Okay? So we know we have to do something about describing classes. So there's something called a class diagram. Complex classes, a lot of times, will have state associated with them. And so there's a notion of a state diagram or transition state diagram. That's often used as well. I mentioned this in passing. We're actually not going to deal with that today. We're just going to look at the class diagrams, but that's another common representation. And then the last one is you're going to detail how the components interact, so that the proof that you've got this design right is that with the components that you've described, and the components will have both attributes and methods. Can they interact in a way? So in other words, one component can call another component because that second component has a method that will do something for it. Can they interact in a way so that you achieve the use case, achieve the goals of the system? And that's really in a nutshell what this is all about, and which is so powerful because now you've gone full circle and you've shown you have designed a system that achieves the goals. And that's what you want. All right, and there's something called the interaction diagram here. Now, this, like any sort of, everybody here is taking like a class in discrete math where you do proofs, okay? And from that experience, when you do a proof, it's not like you literally go through and figure out each step and then, aha, QED, I've got it right. Almost certainly what you're doing is you have sort of a gem of an idea, and you try a little something, and you try one time through and say, well, wait a second, it fails here. I've got to go back. You're iterating. You're going through, and it's a creative process where you try some stuff and you go over and over again. It's the same thing here with the design. To some extent, you could argue the interaction diagram is the proof that you've designed the system, chosen the right components. That means the right attributes and the right methods so that they can actually do the use cases. That's your proof, that interaction diagram. It's iterative. Yeah?
So if you have, so in the last slide you referred to object interface.
Yes, right.
So you actually like manually define those?
Yeah.
Or is it kind of a property of the object itself?
Okay, so the object interface is really, it's a more of a concept rather than something that executes. It tells you how it is, what does that object do? For example, does that object like in Michaelis-Menten, does that object have ability to estimate Vmax and Km? Right, so that's what's meant by the object interface. Did that answer your question? It's not something that's automatic. I mean, it's really more of a concept. It's you as the designer are saying, here's the way you interact with my object. Okay? All right, and then sometimes what you'll find is you get to the interaction diagram, and there's one of the use cases you can't do that because there's something you can't, there's no method to do it. So, and then you go back and you put in that method. So this sort of flow here is encapsulated in something called the Universal Modeling Language, or UML. Anybody here UML? Ever heard that before? Okay, it's a very computer sciencey thing, but it has a sort of broad application. I actually use UML diagrams in my molecular biology class, not because of software, but I'm describing molecules. And that works really well for computer science students and really badly for biology students because they don't know what UML is. But we're not going to go deep into UML. I do have some pointers, some literature that you can look at from the page, from the course syllabus, and it encompasses all these diagrams. Okay, so what I'm going to do now is I'm going to go through each one of these diagrams and talk about sort of the flow that you use to go through it. And then we're going to make a transition, say, okay, now we understand what the diagrams are, what they mean. Let's see how we write code based on those diagrams. Because that's where I think that's really got to be the first step. You've got to understand where the values, doing the design without understanding how it relates to code is sort of empty. You don't know where it is. So, okay. So what a use case is, it describes how you interact with a system and for what goals. So, I mean, typically the way these diagrams are drawn is they'll have some sort of stick figure person, and that stick figure person will have some sort of a role. So this is an analyst. And in some design methodologies, they'll go to a lot of detail to try and figure out what does that stick figure know and what don't they know. For example, if you're looking at a car, and designing a car and how you're going to interact with the car, the fact is that in this culture, we have certain expectations about a car. If you went back 200 years ago where people had not seen a car before, they're only used to driving maybe a horse-driven carriage, you might design a car altogether different to make it familiar. You probably have something that looks like reins, and to stop the car you maybe want to pull back because that's what they're used to, right? So depending on who that person is, their level of knowledge, what they want to achieve, you will design things differently. And that's why it's a lot of times important to come up with detailed descriptions about the person, what they know and don't know. Then there's a question about these circles over here, what they do. So all I did here, this was actually pretty straightforward. On that earlier page, we talked about lab informatics. I said, what is our lab doing? Well, we're doing enzyme analysis, we're doing flux analysis, and we're doing reaction rate analysis. Okay, and so that's really as far as this diagram goes. And you can put a lot more detail around this, which is useful. But what you would like to do then is get enough specificity so it's really clear about what you're trying to build. Okay, and so one way to do that, one part of that is you can say, okay, well, what's the output? This analyst interacts with the enzyme analysis component. What's the result? Or with reaction rate analysis, what's the result? Maybe it's a couple of plots, And as specific as you can be at this point is really useful. This is another example of where design helps and this methodology helps because you can imagine, your PI says to you, well, Joe, I want you to go out and do an enzyme analysis thing. And, it may take you a couple of weeks. Rather than taking 2 weeks and coming back with a plot that he didn't want, why don't I first go out and just, dummy up something in MATLAB and say, is this the plot you want? There's no data behind this, but tell me if the axes are right, tell me if the labels are right. Oh, no, that's not what I want at all. I want to see it as a bar plot, or I want to see something else. So by doing these kinds of what are called mock-ups, you can save yourself a tremendous amount of time. And so it's a useful exercise. All right, so the more detail you can put into this, really, usually the better off you are because when you get to the level of programming, it's much like if you're building a house. And you're probably too young for this. I assume none of you have had the experience with trying to build a house. Okay, you get killed with detail. So the first, you think, oh yeah, go off, just do reasonable stuff. Well, okay, well, what's the pattern you want for the countertop? And do you want that beveled or unbeveled? And what sort of fasteners should we use? And oh, by the way, what's the size of the kitchen sink? But we have this oval style, but then that won't go with this countertop. You get absolutely killed with detail. Software is just as bad, if not much worse. There's so much detail that managing detail is really a challenge. And that's why if you can be as specific as possible here, and ideally, and this is one of the things that's also very challenging, if you're talking to someone who is your user and is not a computer person, you really need to give them this kind of detail up front so that they can react now, rather than you go off and spend months, weeks, or years building a system that's the wrong thing. Because people don't know, they can't specify in advance. There's too much detail, they can't tell. Okay, so give you an example about the kind of detail you'd like to include in a use case. So the core questions are, what information does the user have to provide? And how does the system respond? Okay, those are the key answers, key questions you have to address in the use case. The more specific you can be with this, you can see the better off you're going to be in terms of writing it, because otherwise you get to writing code and you say, wait a second, is that a line plot, a bar plot? Does it have marks on it? What kind of marks does it have? I'm not so sure. I never asked them that. So, all right, so maybe in the system it could be just something very simple, that maybe it's just done all of the command prompt. And so I say here at the bash command prompt, I say bash enzyme analysis, and I'm going to run it inside a shell script. Okay, and it's going to come up with this little header over here, and it's going to have this right caret, and it's going to say enter the CSV data file, because that's input to my analysis. And then I enter the file, and it says proceeding with analysis, and ... Why did I put the ... in there? Okay, when you're on yeah, go ahead. Exactly. Makes the user feel like something's happening. Very important. What is so frustrating about a system that takes time? You have no idea if it's lost in outer space or it's actually doing something. There's a very technical term in the computing industry for these kinds of things. You've seen other things too, like a progress bar. There's a technical term. Anybody know this technical term? Thumb sucker. Very technical. Yeah, and that's exactly it. You want to, sort of like a way of passing time to let you know the machine's actually doing something. And it's also very important to tell it when you're done. Now, maybe there will be obvious output, but depends. And then, then what does the plot look like? All right, okay, so I spent a little bit of time on this part because I think this is often overlooked. And if you don't have the use case described in some detail, what your inputs and outputs are, it's very hard to do much in the way of detailed design because you don't know what you're designing for. It's sort of an abstraction. And what tends to happen is people do something, but it's not necessarily what is desired, and so the whole process of building that software takes much longer because you're doing the wrong thing. The other thing which I will emphasize is that there is just limits to the level of detail people can absorb, and so it's very reasonable to do something simple first and then ask for refinement. So it's not like you're trying to get everything right at once. Okay, so let me go on to the next part here, component specification. We'll spend a lot more time on this because this is, so now we're assuming we have our use cases in some degree of detail. We want to now actually start building something. And so these components, what we're going to try and do is get it sufficiently detailed so that somebody can build it. So we know our components are going to be objects, and we define objects with what? How do you describe an object? How do we do that in Python? Begins with a C. Class. We do our class definitions, right? As classes, objects are instances of classes. So we know what we're going to be talking about here in this part of the design is we're going to be talking about how do you describe a class. And there are various different ways that you can do this. So what could you do? Okay, so we could describe our classes in English. And English is always a fallback. I don't want to discount English. The problem with English is it's very easy to misinterpret. But it's a good fill-in. Have you heard the term pseudocode? Yeah, pseudocode is that you write something which is essentially a stylized English. If I wrote down, instead of writing the specifics of a for loop, I'd say, for every element of this list, I'm going to do the following. That would be sort of a stylized English, and it's close enough to actual code so that I can translate it. So that's a key part of any sort of specification technique, is I have to be able to easily translate it and precisely translate it into code. Because if I can't do that, the specification doesn't have value. And the last one, which is what we're going to use, is what are called class diagrams. Anybody heard of that? It's part of the UML structure. Okay. All right. And there's also state transition diagrams, but we're not going to do that. Okay. So let's start about how we're going to develop these components. The first question is sort of a basic one. Like, what components do I need? It's sort of like, okay, I see this enzyme analysis we're going to do, but what components are needed to do that? And I sort of have to think about that for a little bit. Now, once I've done that, I'm asking a second question. Well, okay, I've sort of sorted out the components I need. Are there things that I could just pick off the shelf, like in Matplotlib, or from some control toolbox or something else? And then, okay, well, some of these components I can't necessarily get off the shelf. And what do I do there? Well, then I may have to actually create some other components, identify some other components that allows me to build the things that are missing. And hopefully at some point I'm going to get to the point where I have something that I can use. Because if I've got to end this sort of recursion somewhere. Somewhere I've got to get to the point where I can start writing some code. Okay, and then I do these things iteratively. So let's see, and let me go through this. And so here's some examples of for those 3 use cases. Here's some, sort of some initial thoughts I put down about components would be useful. Okay, so for enzyme analysis, chances are the data's in a CSV file. It'd be really nice to have a component that could read CSV files. That sounds like a really useful thing to do. Now, whether or not this is what I actually end up using or needing, that sort of depends. The proof will be had when I do the interaction diagrams and see if I can actually do the use cases. But for right now, that seems like, again, this is sort of a creative process. You make some guesses, you try it, you iterate. Okay? I probably need something that estimates the Michaelis-Menten parameters. I probably want something that fits curves. Maybe I need something that looks at for the Michaelis-Menten, and maybe something that just plots a curve for the reaction rate as a scatter plot. If I look at the flux analysis, well, I probably also want a CSV file reader. That's probably where my data is. And I probably want something that does flux estimation. Maybe that's too big of a component. I may have to break that down a little bit. And similarly with reaction rate stuff. So this is typically the place you start. You look at all of your use cases. I had 3 use cases. And you start putting down, roughly, what do I think I need? And again, because it's a creative process. Okay, then let's sort of, what I'm going to do at this point is I'm going to drill down to a particular part of this. And I'm going to, hang on just a second. Something just occurred to me. And I hope, okay, let me see something here. Okay, all right, good. I had this uncomfortable feeling for a second that I had not started the recording. You know how it's sort of like, the student dreams too, where you wake up and you think, oh God, there's this class I never dropped and I have the finals due today. Yeah, that type of thing. All right, let's see here, get back to this. Okay, here we are. All right, let's go back here. All right, okay. So, let's drill down on this one component, because CSV file reader was something that seemed to be used throughout. And again, what I'm trying to do is give you a feel for how you design these components. What does it mean to specify them? So CSV file reader, it's used in all of them. Now, one of the first things you want to do to try and figure out what's in this component is you want to figure out, well, what are the requirements? Well, the requirements come from the use cases that component has to satisfy. So I want to use CSV file reader for all 3 of those use cases. So that's for enzyme analysis, for flux analysis, and for reaction rate analysis. For enzyme analysis, I'm going to have 2 columns. I'm going to have the substrate and the reaction rate. For flux analysis, I can have n columns. And then for reaction rate analysis, maybe I only have 2, but one of them is a special column. It's a time column. Actually, for enzyme analysis, it's also special too because I have to have substrate and reaction rate. Okay, so if I do this as CSV files, it's pretty generic. I have label column headers, so which are strings, and I have data underneath it. So if we look at then what this does, here's my so at this point then what you've done, again, this is sort of a creative process. I've seen which use cases I'm going to need this particular component. I've sort of figured out roughly the requirements, and now what I'm doing is I'm being more specific about what this component does. So this component has to read a comma separated value file. It may have n columns in it. It's going to provide a list of the column names, so that I know what's there, and I want to get data for each column. Okay? That makes sense so far? Because we've actually gone a very far way, and this is part of the process, this whole thing about design, taking this grand idea, starting with, a PI says to you, I want you to do some enzyme analysis, to, I've got this component, CSV file reader, I'm going to build that. That's actually a big way, and this is some of the things where I think that, as self-taught programmers, you probably have not thought about it this way, and managing this large amount of detail is really what sort of separates the people who are skilled with software with those who will tend to just do small things in like a command prompt environment. So this is a pretty fundamental kind of thing, even though we've gone through it fairly quickly. Okay, so now I'm actually pretty close to designing this component, because I've figured out what it has to do. Once I've figured out what it has to do, then I might ask myself some other questions like, okay, well, this is pretty simple, but does it satisfy all the requirements? In other words, for Michaelis-Menten, I have to know which column is the substrate and which column is the reaction rate. How will I know that? And for the reaction rate analysis, I have to know which is the time column and which is the reaction rate column. So how am I going to know that? Any thoughts about how I could do that? I mean, at this point, I haven't written any code. I haven't even done any design other than putting bullet points on a slide. So I have, pretty much a blank piece of paper. I mean, I can do this many different ways. Any thoughts about how we're going to address those requirements? Are we going to do that in CSV file reader, or are we going to do that some other way? Any thoughts? Okay, well let's take it around this way. Okay, what if I make CSV file reader more functional so it knows these things? What are the implications of that? For example, I could always say that, gee, the first column is going to be time. All right, if I do that, what's the problem with saying that CSV file reader expects the first column to be time? What's my time column in flux analysis? I don't have one. Right, that's a problem. Okay, so CSV file reader would then not be applicable there. I have something more specific that's probably for reaction rate analysis. So these are the kinds of things you have to think about at this stage. Have I really specified what this thing is supposed to do? So my feeling about this, and again, you iterate and you try and you see what works, is one way to do this is that to handle this is you could have a naming convention. Something that's called time is time. Now that's part of your system then, because now someone creates a CSV file for reaction rate analysis, they have to have one column with the label time. Okay, so it may also be that I have a similar problem with the enzyme analysis, where I need a column which is reaction rate, and then I have some substrate. I mean, I don't know what the name of the substrate is, but so if I always say that the name of the reaction rate column is V, I've solved that problem, but that's a specification system. That affects my use case. When someone is doing the use case for enzyme analysis, they have to create a CSV file with the right format. Okay, that makes sense in terms of, because see, designing a component is both about talking about what it does do, as well as talking about what it doesn't do. CSV file reader will not tell you what the time column is. That's a higher level capability. The caller of CSV file reader has to figure that out based on the column names. And CSV file reader will help the caller. How? How will CSV file reader help the caller with figuring out which is the time column if my way to specifying time column is to have the column labeled time? How will CSV file reader help them? And I'll give you a hint. It's this bullet right here. Exactly, right, display, or I can interrogate it, because this is a program, right? And so in my program that's calling this, I want to figure out which time column is. It will allow me to interrogate that file and say, give me the names of the columns, that I know which column I need to get. Okay. All right, so now we're going to figure out what's in this object. All right, so we're going to describe classes. And this time, instead of describing classes using a Python syntax, we're going to do it with these diagrams. There's a sort of standard form to these diagrams. So I'll give you an example of this kind of thing over here. So in this diagram over here, this header up here, they're always in these three sections. So this up here, this header up here, gives the name of the class. We're creating classes. That's why we're going to describe the instance of the objects. They're going to be classes. So there's a CSV file reader class. Here are the attributes, and here are, what are these? You know what this is called? This section over here? These are methods. Remember, classes have attributes and methods. Just a second. I'll get it. Okay. So when we talk about specifying a class, we're really talking about specifying three things. First one is pretty easy. What's its name? Okay. Then we have to specify its attributes, and we have to specify its methods. And that is all you need to do a specification of a class. In fact, from what we talked about in the Python object-oriented programming discussion, you pretty much know how you would write what's called a stub, or a sort of simple method, a simple class, or skeleton for a class. In Python, you would say class, and you would put in this name. And then you would have in the underscore init method, self.filename equals file name. Because it's probably one of the arguments to init, and columns is an argument, and data is maybe an argument. Or at least they're internal variables that may or may not be arguments. And then here, you would have a method called read, and you would have, def read and def column name and get column names and so on. So it tells you pretty much how you're going to write the code. All right. So like I said, these are attributes as columns. Now, so far so good. With these diagrams, we can actually take this a step further. What is it that we could provide that's more detailed than we've got right now, and would be really helpful to us when we write the code? Yeah, what types? When you say types, what types of what?
For the attributes.
For the attributes, excellent, excellent. For the type, okay, that's very good. How about for the methods? Where can we incorporate? You're on exactly the right path. What could we do with type information for methods? Where do types enter in methods?
The return type.
The return type, excellent. And what else? What other types? What else does a method have? A method may not have, may have one or more arguments. Right. So we want all of that. If we can get all of that in there, we've got a tremendous amount of information. And I apologize, I went through this a couple of times, and so I sort of edited different ways. So, so what do we got here? Well, file name is a string. That's easy. The columns, okay, there's maybe more than one column, so it's not just a single string. It's a list of strings. Okay, and then the data, well, the data is the data consists of the data for each column. Each column has more than one float, so that's a list. And it has, you have to have some way of identifying it. You could do it by the order. I did it by the name. So it's a dictionary, and remember, a dictionary is a sort of associative memory data type in Python. And so I could say, for example, the column associated with reaction rate, which is going to be V, that's going to be that string V, and then I'm going to have a list of floats. Okay, does that make sense? Now, if we get down here to the methods, it becomes a little bit more involved. Read has no arguments. Get columns, names. Ooh. Okay, that's actually a bug. What's wrong with that? This is really good. This is a case of a design letting us know right away there's a problem. Get column names. What's the return value for that? String. What's wrong with that? Okay, so I'm sorry? It should be a list of strings. That's actually a bug, right? And that's actually, so this is something we could see right away, that is a bug. I'll fix that in the slides. Okay. Now, how about the last one there? Get column data. Okay, does that make sense? So it's parameter, it takes an argument, which is a string. What will that string be? What's the semantics of that string? It's going to be a column name. And it returns what?
The list of the data.
Exactly, a list of the data for that column. Okay, so we actually have a lot of detail about this. I mean, we're pretty close to knowing how to come. We'd have to figure out, what the logic is in each one of these pieces. Which of those methods, which one is the most complicated to write? Get column names? Okay, these are the methods. Methods are here. You got a choice of these three. The third one, get column data. Okay, it could be depending on how you're doing it. Okay, so it depends on how you write this. Any other thoughts about what might be the most complicated method to write?
Another one could be read,
Okay, why would read be complicated?
because you got to set up how you're going to iterate through each one of the columns, and you got to find a way to separate each column from one another and read through the data.
Okay, and then once you got finished with read, what would you have? What would be the result of read? Now, read has no return value, so what it's probably going to do is it's probably going to update some of these. These are state or internal attributes. So what do you think read might do? So so on the constructor, you're going to specify the file name, and then read might create the columns variable or the columns list of strings, and then the data dictionary. So if read did that, then again, it depends on how you write this, and we haven't talked about how you write it. If read did all of that, then get column names would be pretty easy, right? It's just returning this, because that's a list of strings. And then this over here, get column data, what it would have to do is it have to look up for that particular, I should do it over here so it's visible. It would have to, okay, so this is get column names. It just returns this, it should be a list of strings. And then over here, get column data. What that's going to do is it's going to take one of these column names as an argument, and it's going to return the associated list of float for the value of the dictionary associated with that. So those could actually be pretty simple if we implement it this way. But we haven't really talked about exactly how we're going to implement it. But that would be my sort of bias. My guess would be the same, is that read would be big and the other two would be sort of small. All right, so here we have the data types. Now, let me at least briefly talk about another thing that commonly happens in design. This is such an essential part of design. And that is, you started out, remember we started out with that chart initially where we associated various, what we thought might be classes or components with the different use cases. We had that little bubble chart. Okay, what often happens, that's sort of like a first stab, our best guess. We've got this proof we're going to write. We sort of think it's going to be by, some sort of, induction, and, we haven't got it really right altogether. Well, what often happens is in the process of figuring out your design, and you've got this set of classes you're going to describe, you discover, gee, you know what? I really would like to have something else. And so you discover a new class. So, for example, here, what we see is, well, if we look at this CSV file reader, what have we got? Well, for each one of the columns, we have its data, and then we have its name. And we sort of have separated these things out here. And another thing is that we might want to try and combine them together. And so that we have the notion of a variable, where a variable combines together the data and the name. We sort of have that pretty close here with the dictionary, but it's sort of combined together. So we could potentially define a new class called variable. It's not required, but a lot of times it's convenient, and you'll find it, if it's reused a lot, it's particularly valuable. So what this represents is the entirety of a column. So it's got a name and a list of floats. Now, it's really up to you when you think it's appropriate to introduce a new concept. it will seem natural when you find that that concept is reused in other places. That class is reused in many places. The other way you'll see it's very natural is when you try and describe this to someone, describe your design, and you naturally use the term variable. And I say, what's a variable? Well, a variable is a name and a list of floats. Okay, and so if we do this, and we go from this design to this one over here, and the big differences are where the circles are, that now suddenly, instead of returning this sort of thing which is just a list of floats, we actually return something which is an integrated whole. It's a variable. And over here, we have variables that we're containing rather than just the individual values. Okay. All right, let me go past this because we're running a little late on time. All right. Now, here's another thing that happens very commonly in design, is you'll recognize that one piece of functionality can serve more purposes if you organize it right. So you remember in the original one we thought about enzyme analysis and then reaction rate analysis, and actually even the enzyme analysis involved plotting the raw data and also plotting the fitted curve. So we're doing a lot of plotting, actually. I mean, there are 2 use cases. We have plots. In one of those use cases, enzyme analysis, we have a couple kinds of plots. Gee, does it make sense to have a separate class that just does plotting? So maybe we want to do that. Maybe there's some standard fonts we want to use. And rather than repeating that over and over again, we could have that in this separate plotting class. And so what the plotter class does is it specifies the fonts. You get the title. You get the X and Y variables. There's some standard methods you use. And then so enzyme reaction plotter is just something that inherits from this. Remember, inherit means that it's like we took all of these capabilities and put it in here. And it has a much simpler interface, the way you use it. Okay, so and what we would find is that that's the enzyme reaction plotter. There would be a separate one for just reaction rate plotting, and they would all use that same capability. So that ability to inherit, and that's what this upward arrow over here means. It means that in this class over here, you will find all of these attributes and all of these methods. Does that make sense? I know it's it's a warm day and there's a lot of stuff we've been going through, and so I'm trying to get a feeling for what's there. Okay, so the complete diagram, what's called a class diagram, which describes the design, is something like this. Where, for example, in this case, we have one superclass here called enzyme analyzer. That's responsible for implementing the use case. Okay, that class and these diamond things here means that it has this other class, or it knows about a member of this other class that it uses. So the enzyme analyzer, it has a class CSV file reader that it knows about and it uses. And it has this Michaelis-Menten estimator class. And over here it does some plotting. And that sort of seems like the right kind of stuff. We see that CSV file reader uses this notion of a variable. That's a new class we created. Turns out Michaelis-Menten, it's really useful to have it there because you have some variables here too. What are the variables in the Michaelis-Menten analysis that you're concerned about? You've got the substrate and the reaction rate, right? So those are variables, okay? And then the plotting over here, and then the plotting part actually is something that's useful as well. That's interesting. There's actually a bug in this design as I've described it here. Does anybody see it? See, what I wrote here was that the reaction rate, the enzyme analyzer knows about plotter. It actually doesn't know about that. It knows about enzyme reaction plotter. So this line here should actually be down there. Does that make sense? Because that's what it actually uses. And I will fix that. Okay. All right. Okay, so hopefully those pieces make sense. And let's go down to the last part here. This is for the interaction diagram. So this is so now what we've got the thing we're trying to do, which is the use case. And hopefully we've done that in enough detail so we know what we're trying to do. We've got these components we're going to describe as classes. And then the last part is the way we make sure that we've got the classes described, the right classes with the right kinds of methods and attributes, so that then we can actually do the use case. Okay, here's the way these interaction diagrams are usually done. You've got to start somewhere. So I start with something called user. I mean, you can start with almost anything, whatever you say. Who's going to interact with the system? That's what this corresponds to. So somebody start, and what it typically will be is it'll be like a main program somewhere. So what it's going to do is something's going to start this off by saying, I want to do enzyme analysis for this file, this CSV file. We'll call it, 09 underscore thdpa.csv. Okay, so that's what gets fed in here. Then enzyme analyzer says, fine, that's great. You know what? The first thing I have to do is I have to read that file. Well, I'm going to have to create an object, a CSV file reader object, and how do I do that? Well, I have to do a constructor, and the constructor is I do an init with its file name. How do I know its file name? It was given to me, right? So here's a great example of if enzyme analyzer does not have an initial constructor that specifies the file name, there's no way I can do this. So that would be something you might describe from design. Okay, and then these interaction diagrams are all about drawing these lines between objects of classes that you have specified. And you can only, and the rule is you can have a line from one object to the other with a label, only those labels for which there are methods, and only those arguments for which you have data. And this is sort of a formal way of making sure that you've got all the information you need to do what needs to be done. All right, so here's an example here for enzyme analysis. This is for part one. This is just for reading the file. So we saw before we do the initialization over here, and it says analyze. I mean, I guess it depends on what point at which you do this call. So here it comes after the analyze. So it's actually going to create the CSV file reader object, and it does a read. Okay, so it's going to read the data, and then it said the enzyme analyzer says once that object is created, read all the data. Now that the data has been read, it can get the column names. Okay, so why does it need to know the column names? We're doing enzyme analysis. CSV file reader, does it tell us which column is the substrate and which column is the reaction rate? It doesn't. We have to read the column names and look for, we decide we're going to look for V because that's our reaction rate column. Whatever is V, we've got that, and then we know the other one must be our substrate, whatever that is. Okay, so there's some logic in there that it has to know about. If it's got the column name, so it gets one, and then it gets the other. It signs the substrate concentration. It gets the data associated with that. And then creates a variable over here as well. Okay. All right. So if you go through, so the way these are, these headers over here, the way it's done is this is the class name. So remember, the class is the template, and anything with a dash and a number after it is an object of that class. In these cases here, you'll only see one object for each class. In general, you can have many objects for the class, and so it's dash 1, dash 2, dash 3, and so on. That way you can show more interactions. And here's where we create the object, you call the method, you return a value, and then there's some internal processing over there. All I'm expecting is you can read the diagram. I'm not expecting you to write it. All right, so here's the second part of this. Okay, so now we've got all the data. Now we have to estimate the Michaelis-Menten parameters. Okay, so how do we interact with that object? Well, you have to pass it these variables for the substrate concentration and reaction rate. You say calculate the parameter. That actually is one of the methods. Again, you remember the rule. There has to be a method here in the Michaelis-Menten estimator class that says calculate. And if there is, then we can do this. And then we can separately, one thing you could do is just returns those values. The way I did it was then you ask for them. So it asks for the Vmax, it gets it back. That's what the dash line is. Or asks for Kn, gets it back, and then it's going to create the it's going to do the plot. And the plot class has two methods. You've got the constructor and then actually doing the plot. Okay. All right. And so. Okay, so then what I've done in this particular case for the plot, the rest of the methods over here have to do with the details of adding the plot. So the way I've done it is you specify the y variable because the plotter knows about that, and then you fit the curve, you do the, so this is a curve fitter over here, so it'll actually return data then that you can add to the plot. You add that to the plot over there. Okay, so this is all for the enzyme reaction rate plotter. Okay? All right, so given the time, I want to get onto one more piece here. I'll just say that, the kinds of things that go wrong where you end up with a design like this, I mean, it's all this is all about judgment. Okay, so you can make the design too general, you can make it too specific. You can make it too many classes, you make too few classes. Too many, too few interactions. You're looking for something that, is manageable. And so it just requires judgment. Let me get to this last part over here, and that is, okay, we've done all this work with design, then how is it that we actually build something? Okay, so we know what the starting point is for this. All right, let's get out of this for a second. So the starting point for all this is going, let's see over here. All right, so the starting point for all this should be the class diagram. So let's start right here. And let's make this a little bit bigger. Okay, let's look at enzyme analyzer, and let's see, let's do this first. Okay. All right, so let's see, we've got enzyme analyzer. And can I make this just a little bit bigger? Yeah, I think I can. See if this will work. All right, good. Good, that's what I would like. Okay, so we want to go from this specification over here to code. Okay, here's a file that, yeah, I guess it's somewhat readable. Here's a file that then describes that. Let's see if I can get this a little wider. And so you always see it all. All right. Okay, so we're going to then build this a file here. It's going to be a separate class, so enzyme analyzer should be its own class name. Then the common way of doing this is that the file names are all lowercase letters, and the eluding together here, instead of having a capital there, you put an underscore. So it's enzyme underscore analyzer.py. That's sort of a common way of doing this. What you care about is then, how do I define this class? Well, my starting point, I know the class name. So I'm trying to now write code for my specification. My specification are these class diagrams. So I'm writing the code, and so right away I can write this first line right away because I know the class name. The class name is enzyme analyzer. Okay. Now the next thing I have to do is I have to write the underscore init method for the constructor. Well, the main thing I need to know for the underscore init, underscore init underscore is what are the arguments, the parameters that are passed to the constructor. Well, what is it? The file name. Okay? So right away I can write that. I mean, it's an instance method, so it always has to have self in there. Now the next thing I need to know is, okay, so what are the instance variables, these are attributes, that I need to define, the self dot variables. Okay, and so in this particular case here, which actually, okay, so this design is actually incomplete. It probably should have been done a little bit better. So that's actually a good thing. It's something you can refine as well. There are some internal variables over here, substrate concentration, reaction rate, that are defined over here. Those should actually appear over here too. So a good design, if it's designed, and maybe on the first pass you wouldn't have included those, but if this specification was done correctly, you should do that. And so that's the way you would do that. So that already gives you this method. Then for analyze, over here, okay, analyze, you know how to write that. That's a method. So you write it just def, analyze, and then self over there. And at least you've got that skeleton. Now, after that, to figure out what else analyze does, you have to look at the interaction diagram. Right, so we go back to the interaction diagram, and we see what it is that analyze actually does. Because that will then provide us with a way of then figuring out what should go next. So we see that analyze, so we call it the analyze method here. It's going to create a CSV file. So we know that that has to be done right here. And we just follow the diagram through step by step, using those same procedures with making sure that we've got the right components implemented. Okay, that makes sense? Okay. So at the end of the day, what you can do here is, without writing any real logic, in any of these methods you've created. It's more just like a skeleton. You just want to make sure it calls the right thing in the right order. If all you do is just say print, and I've got this method here that this is basically just print. There's a separate method that gets imported over here called report in a utility thing over here. By the way, all this is in shared code in a repo. So that's just going to say, I got to this method, analyze. So what we should be able to do is then run this program and be able to see how close we get to this interaction diagram over here. So if I'm going to make this a little bit smaller so we can actually see it. Okay, so what should happen is we should see enzyme analyzer gets called, it gets initialized, we then start calling CSV file reader if these print statements work right. Okay, so you see what happens. Oh, good grief, that looks horrible. The quality on this is, well, okay, I'm not going to fiddle with it too much. But what you should be able to do is then, if you put print statements at the top of each method, you should be able to make that look like the same sequence you're getting over here with the interaction diagram. So now what we've done, and the key thing here, is we've taken from the design specification by just doing what's called a skeleton implementation of each method, where all we've done is basically do a print with no logic other than making sure you call those methods and other objects that you need in some order. Then we should have the same thing that corresponds to our interaction diagram. That's a way of showing that now we're on the right track with doing our implementation. So we go back over here and let's see here, go down a long ways here. Okay, and we've done the skeleton implementation, shows what comes after design. You do this skeleton implementation, okay? And so your homework is, I've done the first one. This is in shared code. You can see how it works. You get to do the other two parts, 2 and 3. You get to create the classes for the plotter and the other piece. And I'll update the diagram so that it looks right. I've got the diagram specified wrong. Okay. If you have questions, come to office hours. Okay? And I think you've probably, I realized I was a little bit rushed towards the end because of time. The other thing that I will do is, in addition to this video, I will do, I'll tack on another piece of video to go through this a little bit more carefully, because I think that will help you. Because I can tell that this last piece here about using the specifications, that didn't go quite as smoothly because I was a little bit rushed. So I will do that as well, so you have that on the video. And definitely come to office hours if you have any questions. Okay? But I think that you will find that by interpreting one of these diagrams and writing this skeleton implementation, you will have a really good understanding about what a specification is, an object-oriented specification, and how to use it. Because that's the first step towards them being able to do your own. Okay? All right, great. All right, see you on Wednesday.